Hi everybody. This is lesson 8 of solar energy application course. Today is the last session for solar radiation. Actually it is part 7 of solar radiation, which will be finished today, and from next lesson we will start other topics. Okay, as mentioned before, this is our textbook. Pictures and many texts are taken from this book, and whenever there is another reference used, it will be mentioned at the bottom of the page. Last week I talked about solar radiation modeling, among them Angstrom-Prescott model and Clearness index definition and application we discussed about, and the same topic will be continued today, covering the following items: modeling direct and diffuse radiation on a horizontal surface and solar radiation on a tilted surface, which is a very important topic and actually our last target in this section. Okay, if you remember, clearness index is defined as the ratio of the terrestrial radiation to the extraterrestrial radiation. Terrestrial radiation, as you may remember, is the radiation on the Earth's surface. Extraterrestrial is at the top of the atmosphere, and the ratio of terrestrial solar radiation to extraterrestrial radiation is named clearness index, which in some way show you how much of the red color here reaches the Earth's surface. The ratio is between 0 and 1, and it's clear that if it is towards 0, then you have a lot of things in the atmosphere, from clouds, dust, or maybe anything else. And if it goes towards 1, it shows that it's a clear day without anything in the sky. If you remember, we have 3 types of clearness index, or clearness index may be given in 3 forms. The first is, let's start by this, daily clearness index, which is shown by capital K with a subscript T, which is the daily the solar radiation on the Earth's surface, H, to the extraterrestrial radiation, or daily extraterrestrial radiation. So this is for a day. If you remember, H is the radiation from the sunrise to the sunset, and the nominator is the solar radiation on the Earth, and the denominator is the solar radiation at top of the atmosphere. Now, if you take an average for the month in question and calculate the monthly average, but again daily clearness index, it is shown by the same in the same manner, but with a bar over K. And as you can see here, H is here the monthly average daily radiation on the Earth's surface for the month in question, and H bar 0 is the monthly average daily extraterrestrial radiation. So this is the daily clearness index, this is the monthly average daily clearness index. This is for only one day of the month. This is for any day for the month. It is clear that this one is more accurate, but you can see later that it may be difficult to calculate do the calculation for all days. But in some cases it may be necessary. Even it may be necessary to calculate to do the calculation for every hour of the day. In this case, an hourly clearness index, KT, can be defined, where K here is an italic form, and it is the ratio of the hourly solar radiation on the Earth's surface to the hourly extraterrestrial solar radiation. Today we want to know what is the share of diffuse and beam radiation on a horizontal surface, because in the last session we learned how to calculate the total radiation on the horizontal surface. Now today we want to know how I can calculate the share of direct or beam and diffuse radiation. So let's start. Total radiation on a horizontal surface, as you may remember, is the sum of beam and diffuse radiation on the horizontal surface. Please note that this is not the case for a tilted surface, because in that case, as you will see today, later, There is another parameter also added, but for the horizontal surface, the total radiation is the sum of beam and which is equal to direct and diffuse radiation. So, if you have two of these parameters, you can calculate the third. For example, if you have the beam and diffuse radiation on the horizontal surface, simply you can add them to find the total. If you have the total and beam, then you can subtract them and find diffuse. And in the same manner, if you have total and diffuse, then it is simple to find the beam radiation. So, suppose that you have, this is the general case actually we are looking for, you have the total radiation, you have a formula for one of these, beam or diffuse, and then you can calculate the third one. There are a lot of correlations, experimental correlations in the literature, which enable you to calculate the ratio of diffuse to total radiation. These may be introduced in three forms: hourly, beam and diffuse component of the hourly radiation, beam and diffuse components of the daily radiation, and beam and diffuse component of monthly radiation. In this section, section 210 of your textbook, and the following two sections, 211 and 212, these topics will be covered. 210 is started by the beam and diffuse component of hourly radiation. Here you can see some of the correlations which exist for calculating the ratio of diffuse to total irradiation. As you can see, to calculate the ratio, you need the clearness index value. As you can see, this is the italic K, so this is the hourly clearness index. So if you have the clearness index, hourly clearness index, by either of these equations, which belong to different researchers, you can calculate the ratio of diffuse to total. And if you remember, just in the last slide, previous slide, I told you that if you have I and ID, or I and ID to I, then you can calculate I beam. So there are also formulas which are fitted to the curves of these researchers. For example, for Orgil and Hollands, you have this formula, as you can see, because it was not able to fit only one equation to the curve. This is comprised of three parts. One maybe from here to here, the second in this area, and the third in this area, depending on the value of KT, as you can see. For example, here in the middle, you have this correlation before 0.35, you have this equation, and finally for KT bigger than 0.57, the value is a constant value equal to 0.177. There are also other correlations. For example, by Erbs define the ratio as this. So either by the curves or the equation, this is the procedure that we will follow. This is very important. Please pay attention to this. You have KT, where from measurement data, for example, I showed you in the last session, for example, in Iraq, in some cities, you have the KT value. Then you will go to hourly KT value. Then you will go either to the curve or to the formulas and find the ratio ID over I. For example, here you can find it, or by the formulas. Then it is simple to find the diffuse radiation. The diffuse radiation will be the ratio, which is found from curve or equation, multiplied by I, and you will get ID. From where we can find I is either from measurement or modeling. So this is the method which is used in section 210. In section 211, the same will be followed, and the topic is beam and diffuse component of daily radiation. Again, there are a lot of researchers did the same work, and this is one of them from Erbs in 1982. And as you can see, again, you have KT, is capital K, because this is the daily radiation, daily clearness index, and having the KT value as an example. This is just an example from 0.6, then you go up depending on the value of omega s, which is the sunrise or sunset hour angle. You will go to the left, and here you can find HD over H. Again, there are formulas to correlate this equation, this curve, and you may use either the curves or the equation shown here. These are taken from the textbook. Another formula which is also very important is the Clearness formula, and here you can see that there is again a formula to calculate the HD over H. So this is the procedure like the previous one. You have KT value, but this time it is the daily clearness index, where from measurement data generally, or any other resource, but trusted source. Then you can find HD over H either from the formula or from the curve in the previous slide. Then you can find HD in the same manner, and H, as told before, is either from measurement or solar radiation models. And the third section is beam and diffuse component of monthly radiation. Here you can see again that there are a lot of formulas. This is again from Erbs in 1982. Having the KT value, you go up depending on the sunrise or sunset hour angle. Go to the left and you can find the HD over H bar. Or you may use these formulas. Again, this is the procedure. You have the KT value, monthly average daily clearness index. Find the ratio from the curves or the equations, and then you can find the diffuse fraction. Whenever diffuse fraction is calculated, then having HD, having H bar, you can find the beam radiation. Okay. This is the procedure. Select either hourly, daily, or monthly clearness index. It depends on the calculation you are doing. Find the ratio of diffuse to total radiation from available correlations, either formulas or the curves. Calculate the diffuse radiation. Calculate the hourly, daily, or monthly radiation on the horizontal surface from equations which is given here and here. It depends on which KT you used. Let's have an example. This is in continuation of the example in the last session. So, as I noted here, please read the previous example before reading the solution to this example. Why? Because this is in continuation of the previous example. In previous example, I asked you to find the solar radiation on a horizontal surface in Kirkuk in Iraq. This is the procedure that we followed in the last example. We find the Kirkuk latitude, month of the question, for example, it was maybe July, yes. And then we found extraterrestrial radiation for Kirkuk from tables in chapter 1. And finally, we found the terrestrial radiation, total terrestrial radiation on a horizontal surface in Kirkuk in the month of July. It was 23.14. Please read that example. I just want to mention again that please read the previous example before reading the solution to this example. Okay. In example solved in lesson 7, we calculated the monthly average daily radiation in Kirkuk on a horizontal surface for the month of July as 23 megajoule per square meter. Calculate the beam and diffuse fraction of the average July radiation on the horizontal surface in Kirkuk. Monthly average daily clearness index for Kirkuk in July was 0.57. This is also from the previous example. So we want to know what part of this 23 is diffuse, what part is direct. For example, 3 megajoule per square meter is direct, 20 megajoule per square meter is diffuse. So let's start. Solution. Step 1. Monthly average daily clearness index for Kirkuk is July is 0.57 from the reference introduced in the previous example. Step 2. You can use either figure 212.2 or equations mentioned before to find the diffuse fraction. But first you need to calculate omega s, which is the sunrise and sunset hour angle. Why? Because there are two curves or equation and you shall select the right one. Here you can see that either using the curves or the formula, you should select first which is the value of omega s. This is left to you to do that. Please do that and check what is the omega s value for this case. For node, suppose that is larger than 81, so I use the top curve. Please note that this is left to you to do that. Step 3. Figure 2, either the figure or equations may be used, and you can see that having the clearness index, which is 0.57, go up to the curve, to the right curve, and then to the left you can read the value of HD over H bar, which is maybe 0.37 or something like this. Next step, calculate the diffuse fraction from diffuse radiation from this equation. The value in parentheses you can find from the curve, which was maybe 0.37 or something like this, and this is 23.14, which is the total radiation as previous example. So you can find the diffuse fraction, which is the monthly average daily diffuse radiation in Kirkuk on the month of July. Calculating this, and the next step is to find the beam or direct radiation. The beam or direct radiation can be calculated simply subtracting HD from H bar, which is the total radiation. So in this way you can calculate the beam and diffuse share fraction of the total radiation, which is given in the previous example. As you can see, there is no numerical values here. This is left to you to complete the example. Next step is the estimation of hourly radiation. From where? From daily data. As you can see, the topic of section 213 is estimation of hourly radiation from daily data. What does it mean? It means that now in the previous section, for example, last week we calculated the total radiation on the Earth's surface per day. Okay. Now you want to know, for example, what is the radiation received between 9 to 10 o'clock in the morning. You want to know what is the value of radiation received on the Earth between 12 o'clock up to, for example, 4 in the afternoon. This is the meaning of estimation of hourly radiation from daily data. To do that, the procedure is very simple. A ratio is defined as RT, which is the ratio of hourly radiation to the total radiation per day on the Earth's surface. You have this from the previous sections actually. I'll show you a curve or formula to calculate RT, then you can simply multiply them together to find the hourly radiation for the hour in question. Just there is a problem here that you should remember. I showed here the solar radiation intensity or irradiance, as you may remember. You may remember that we had two things, irradiance, and which is the instantaneous value, and irradiation or insulation, which is the energy, and the unit is joule per square meter. Okay, this is the irradiance or instantaneous value of solar radiation. The red one is for a day with symmetric radiation. What does it mean? It means that with respect to the solar noon, the morning radiation and afternoon radiation are the same. This is an example for a clear day, completely clear day when there is no, for example, clouds in the sky. But if it is not symmetric, you can see the blue curve, which is a day with asymmetric radiation, which happens in many days actually, especially in some areas. Here you can see, for example, that here there may be clouds or something like this passing, but in the afternoon the situation may be different. The problem here, I go to the previous slide. Here, as with the estimation of diffuse from total radiation, this is not an exact process. For example, daily total radiation values in the middle range between clear day and completely cloudy day values can arise from various circumstances such as intermittent heavy cloud, continuous light clouds, or heavy cloud cover for part of the day. There is no way to determine these circumstances from the daily total. So please pay attention to this whenever you are calculating the hourly radiation from daily data. The method which we are introducing here is just for a day with symmetric radiation. What's the procedure? The procedure is either using the formula given here or the curves. Either by the formula or the curve, you can calculate the ratio which I showed you here, and then multiplying by H, you can find the hourly radiation data. Here you can see the curve in a bigger size. Generally, just one thing I should mention here is that You can see that half hours is written here. Actually, if you, for example, want to calculate the solar radiation between 3 to, for example, 4 o'clock, then go to the curve belonging to 3.5. And this is the formula which is used for the same. And in the next section, if you want to calculate, I think the topic is wrong here. It should be 214. Please correct it yourself. Section 214 is about estimation of hourly diffuse radiation from daily data. If you want to calculate the hourly diffuse radiation, then again you should multiply the correction factor or the ratio by the hourly diffuse radiation, which we calculated before today. How you can find RD? Either by the formula or by the curve which are given in your textbook. Okay, up to now we learned how to calculate the solar radiation on a horizontal surface, either total radiation on the horizontal surface and the share of diffuse and beam or direct radiation. Now the next important step is to calculate the solar radiation on a tilted surface or a sloped surface. By a sloped or tilted surface, we mean a surface which is at an angle to the horizontal. And as you can see here in a big solar farm, generally in solar energy application, in most of the cases, the panels or solar thermal collectors are not installed horizontally. They are installed at an angle, or they are tilted or sloped. So we want to know how we can calculate the solar energy on a tilted surface. The first thing which is important is that it seems that the number of the section number was not 214 in the previous one. It was in the continuation of 213, but the topic was wrong actually. Okay, when you have a tilted surface, a sloped surface like the one you can see here, in addition to the diffuse and direct radiation, a third is also added, which is the reflected radiation. And as you can see here, ground reflection is added for tilted surface compared to the horizontal surface. So the total radiation incident on a surface consists of beam or direct radiation, which is this, diffuse or scattered radiation, which is this, and solar radiation reflected from the ground or surrounding. The value of the reflected radiation depends on the type and color of the surrounding surface. So, what is unknown in this section? Total radiation on a tilted surface. You have a tilted surface and you want to calculate the radiation on that surface. What is known? Total radiation, and also I should add here, and also the beam and diffuse radiation on the horizontal surface from measured and modeled data. For example, you have a pyranometer maybe here, and you can calculate the horizontal irradiation or irradiance, and then you want to calculate the tilted surface radiation. There are in general two approaches for diffuse radiation modeling. The first is isotropic sky. The second is anisotropic sky. In the isotropic sky model, the sky is considered as isotropic. It means that the solar radiation in the sky dome from every direction is the same, the diffuse part. And in the anisotropic sky model, this simplification is not taken into consideration. So it means that the anisotropic sky is more accurate and maybe more complex. Section 215 discusses about radiation on the sloped surfaces by the isotropic sky. When you have a tilted surface, this is a general formula. This is the general formula for the isotropic model. As you can see here, IT, which is the total radiation on the tilted surface, is the sum of three parts: effect of direct radiation, effect of diffuse radiation, and effect of ground reflected radiation. So this part shows the effect of direct radiation on the tilted surface. This section shows the effect of diffuse radiation, and the last shows the effect of ground reflected radiation. As you can see here, for example, for the first one, it is IB multiplied by RAB. What is IB? IB is, please pay attention, this is very important. IB is the beam radiation on the horizontal surface, and by multiplying it to RB, you can actually make it possible to calculate the share of beam radiation on the tilted surface. ID is the diffuse radiation on the horizontal surface, and by multiplying to the parentheses where the proof is shown in your textbook, you can refer to that, you can calculate the share of diffuse radiation on the tilted surface. I is the total radiation on the horizontal surface. Multiplying by the parentheses and the parameter which is rho g, which depends on the type and color of the surrounding surface, you can calculate the share of ground reflected radiation. The parameter is shown on the next slide. As told before, IB is the beam radiation on the horizontal surface. RB is the ratio of tilted to horizontal beam radiation, which is calculated by the equation in chapter 1. ID is the diffuse radiation on the horizontal surface. Beta is the tilt angle. I total radiation on the horizontal surface. And rho g is the ground reflectance, which depends on the type and color of the surface. So, an important point here is that when you are going to calculate the radiation on the tilted surface, you need the total radiation on horizontal surface, you need the diffuse radiation on the horizontal surface, you need the beam radiation on the horizontal surface. Okay? So, in order to calculate the total radiation on the tilted surface, you need to know the total and the share of diffuse and beam on the horizontal. This is the reason that in the last section or previous sections, we introduced formulas to calculate the diffuse and beam radiation on a horizontal surface. Generally, total radiation on horizontal surface, I, is given from the measurements or from solar radiation modeling. But in many cases, measurement data for the horizontal surface, total radiation on the horizontal surface are available. Okay? But generally, diffuse and beam measurements are not available because in many meteorological stations, beam and diffuse radiation is not measured on the horizontal surface. Just the total radiation is measured. So, if you have the measured data for ID and by IB, use them. I wrote here that from measurement, from measure. But if you don't have the values for ID and IB, measured values, which is generally the case, I can say that in more than 90% of the cases, then you should calculate the value of ID and IB by the methods which introduced in today's lesson in the previous slides. I hope it's clear. If it is not clear, please listen to what I said once or twice more, because this is very important. There's an example in your textbook, example 215.1, which works on the same formula using the isotropic diffuse model. Generally, if you are in the final exam, please note to the topic. If I told that using the isotropic model, diffuse model, you could use the isotropic model. And if I told that using the anisotropic diffuse models, you should use one of the anisotropic models. So here it says, using the isotropic diffuse model, estimate the beam, diffuse, and ground reflected component of solar radiation and total radiation on the surface sloped 60 degrees toward the south at a latitude of 40 n for the hour between 9 and 10 a.m. on February the 20th. Here I is equal to this and rho g equal to this. Okay, the solution. For this our I0 is 2.34 megajoule per square meter. From where? From equations in chapter 1. You may remember that we had equation in chapter 1 to calculate the hourly extraterrestrial radiation for any location having the location parameter. So this is 2.34. The real measured data for that hour between 9 to 10 a.m. in 20th of February is given as 1.04. So dividing I to I0, you can calculate KT value, which is the hourly solar clearness index. Okay, then from the Erb's equation, you can find the value of the ratio. You may remember that there was an equation depending on the value of KT. You can use the equation, or you may go to the curve if you are if you prefer that, but generally using the equations is more accurate. So having the KT value, hourly KT value, which is 0.445, then you should go to this equation because the KT value is between 0.2 and 8. Then you can use the equation, put KT value here, and simply you can find the ratio of ID to I, which is 0.766. Having the value of ID over I by the method that I introduced before and requested to pay attention to the procedure, you can find the diffuse and beam parts of the total radiation on a horizontal surface. Up to now, you have the total radiation on the horizontal surface, you have diffuse radiation on the horizontal surface, you have beam radiation on the horizontal surface. But the story is not finished because still you did not calculate the total radiation on the tilted surface. In order to calculate the total radiation on the tilted surface, you need some other values. Beta you have, rho g is given in the example as 0.6. ID and IB are calculated before. Just you should calculate RB. RB can be calculated from the formulas in chapter 1, and the value is 1.71. Substituting all the values in the equation, you can calculate the total radiation on the horizontal, on the tilted surface given in the example. This part is the share of beam radiation, this part is the share of diffuse radiation, and this part is the share of ground reflected radiation. You can see that the share of ground reflected radiation, even when the value of rho is quite high, because generally the rho value for general surfaces which are dark generally, like cement and or something like this, maybe 0.2 to 0.3. Here it is 0.6, but again you can see that the share of the ground reflected radiation is not so much in the total value. But it should be considered whenever you are calculating the solar radiation on a tilted surface. The next method, as I told before, is the radiation on the sloped surfaces by the anisotropic sky. In the anisotropic sky model, as you can see, this is the sky dome over the solar collector or solar panel. And as you can see in this model, the isotropic diffuse sky in all the sky dome is not considered the same. For example, if this is the sun beam, okay, then you have more diffuse radiation around the sunbeam, which is named circumsolar diffuse. For the diffuse from horizon, it is not equal, for example, to the sky diffuse radiation like this. So the distribution of diffuse radiation from here to the line of beam radiation is not the same. This is named anisotropic sky. Tell it frankly, there are a lot of anisotropic sky models available. I just introduced two of them. For example, you can see more or read more into section 216. The first is the Hay and Davis model. In this model, as you can see, this is the equation. You can see that it is somewhat different from the previous one. Here you can see that something is added here, And here you can see also that a parameter is added here. The third term is the same as the isotropic model. How you can calculate the values given here? AI by the formula given here. So you can calculate the tilted radiation by the Hay and Davis method, by the method shown here. The next is the Reindel method, Reindel et al. Method. And here you can see that again the equation is somewhat different in the first and second term. The third term is the same. Here another parameter is added also, where you can find the parameter as given above. For example, f can be calculated from this. And please remember that you have all these parameters. For example, I is the total horizontal radiation, irradiation. IB is the the beam horizontal radiation. And this is yet an open problem. By open problem, I mean that the research is still ongoing on different models to calculate the solar radiation on a tilted surface. Just to show you, I did a search in Google Scholar for the tilted solar radiation. You can do also the same search with other keywords and see much more. But here I just wrote tilted solar radiation, and you can see that there are a lot of papers available for calculating, for example, a note on diffuse solar radiation on a tilted surface, global direct and diffuse solar radiation on a horizontal and tilted surface in Saudi Arabia, estimating solar radiation on tilted surface with various orientation. This is also a very important point. Let me explain. Up to now, we just discussed about the surfaces which are tilted with respect to the horizontal. A question arises is, can we use the same equations, for example, the isotropic sky, the Hay and Davis model, the Reindel model, the HDKR model, and others, if the orientation of the surface is not towards south? For example, it has an angle with respect to the south direction. It is a good topic for research, I think, if you are interested in doing research, for example, for a master thesis. On this subject, these are still some good topics to work on. When you limit, for example, the search to the papers released just since 2021, again, you can see that there are a lot of papers. Maybe the topics are different. For example, you can see here that this paper discusses about the estimation of hourly solar radiation on tilted surfaces using ANN model. You can see that this is a new model, and the research may be toward the new methods available. Or, for example, correlation formulation for optimum tilt angle. You know, when you find to calculate the optimum tilt angle of the solar panel or solar collectors, again, all these equations we discussed today are needed, because whenever you want to calculate the optimum tilt angle, you first need to calculate the solar radiation on the tilted surface, and when you are going to calculate the solar radiation on a tilted surface, then all the methods and procedures I discussed today are needed. Section 219 discusses about average radiation on a sloped surfaces by the isotropic sky model. What do we mean by average radiation? The formula given before, if you remember, was for the hourly solar radiation. It was IT. And if you want to calculate the monthly average daily radiation on a horizontal, on a tilted surface, then you can use equation 219.1. You can see that it is approximately the same. Just the value of RB, you should use equation 219.3, where omega prime S is the minimum of these two values. So you should calculate both of them and see which is less, and then take that for the value of omega prime S, substitute in this equation to find R bar B, and then other parameters we discussed before. For example, H bar is the monthly average daily total radiation on a horizontal surface. H bar D is the monthly average daily diffuse radiation on a horizontal surface. H bar B is the monthly average daily beam radiation on a horizontal surface. And I showed you how to calculate all these parameters today, so it will be simple to do that. There is a very important example in your textbook, example 219.1, which summarizes all the things we discussed up to this point. I ask you to read this example very carefully. It is a very important example. Please read it, and if there was any question, please ask me later. Now let's summarize. In lesson 1, which was the first lesson, we discussed about various renewable energy types, if you remember. And then in section 2, or lesson 2, we started to discuss about solar radiation, solar geometry, and then to the solar radiation up to today, which is lesson 8. In lesson 2 to 8, we discussed about thermal geometry and also solar radiation. Now, what I expect you is this. I expect you that you should be able to calculate solar radiation on a solar module or solar collector at any slope, at any location in each day of the year. If you are not able to do that, then please start reading and listening the courses up to today. But this is what I expect you to do. In the next lesson, we will discuss about solar thermal collectors and solar photovoltaic panels, which are actually the applications for the topics we discussed till now. Actually, you have the solar radiation on a tilted surface. This tilted surface may be either a solar collector or solar panel. And the next step is to calculate how much electric energy or thermal energy will be produced by the solar panel or solar collector. This is a homework for you. It is a complete homework. Please pay attention to that. Do it very carefully. This is very important homework. It has, I think, about 5-6 maybe, I don't know, 25% to 30% of your final marks. So do it very carefully and send as advised here. These are very important notes. Thank you for being with me. This is the end of lesson 8. Take care and bye.